Okay, so I guess we'll go ahead and get started. Last week, before Thanksgiving, I talked a little bit about LDA, latent Dirichlet allocation. The key paper came out about 15 years ago, and since then, this has become sort of a very widely used sort of practically for modeling text, also mathematically, you know, the ideas behind this model have been used in a lot of other generative models. So LDA is actually very closely related to a naive Bayes model of text. So on the left here is what I put up as a basically explicit, fully Bayesian model of an unsupervised naive Bayes. So the generative story is there's this distribution called a Dirichlet. So this is basically the smoothing parameters, the pseudo data that you're going to use to smooth a multinomial, right? So technically, this is basically a prior over the multinomials. At least mathematically, you can model that. But basically, these are the smoothing parameters for a multinomial. So there's a multinomial, so that means it's a random variable that has k discrete outcomes. And each outcome is a class. All right, so we're going to generate first a multinomial from this Bayesian prior. Then for every document D, we're going to generate a class label for that document. And then for every word in the document, or every position in that document, so so we've got ND, that's the length of the document D. For every word in that document, we're going to generate a word. Okay, and that word depends on two things. It depends on the class label, and it also depends on the probability of drawing that word given the class label. The way we model that is we basically say, well, there's sort of two parents here, one which is the class label, and one which is the set of multinomials gamma. So there's k multinomials, one for each class. So the way we combine these things, the form of that conditional probability distribution where we draw W depending on its parents, it's basically we use Y to index into this array of gammas, and then we choose something according to gamma. All right, and each of these is, again, a multinomial, but it's a multinomial over the whole vocabulary, right? And again, there's some smoothing parameters, and we model this as a Bayesian prior. So we're using the same smoothing parameters for each one of the multinomials. So we just have one beta, which is the prior over those gammas. So this is unsupervised naive Bayes, just drawn as a generative model. There's a generative story for the whole thing. Some of these things are basically a prior with known parameters and a distribution that we compute the posterior over. Some of these are class labels, okay? Some of these things are words. But this is basically the model. And we can vary this model a little bit and get something which is called latent Dirichlet allocation. So here, instead of there being one class, Y, for each document, an unknown class, what we have is for every document, there's a distribution over those Ys. When we're constructing the documents in our generative story, we do the same sort of thing, but we basically draw a Z from that distribution, from each document, and draw a word given that Z. Okay, so here there's one class label for all the words in the document, so it's shared. So it's easy to guess, right? Here there's one class label for every word in the document, so there are a lot more latent variables. We have sort of the same number of multinomials over the vocabulary. So here these would basically be words that correspond to a class. Here we basically have words that correspond to a topic, an aspect. So this is the big difference here. There's one label per document. Here there's one label per word. Okay, and the notation is a little bit different, but that's the basic idea. Okay, so and here again, instead of basically having one distribution over classes, we're basically having to guess a distribution for every document. So this is sometimes called a mixed membership model, because in this case, every word in this document belongs to. It's a member of some unknown class. Here, the words in a document are generated from many different classes. Each of those classes is drawn from this theta d. So a document looks like a mixture of many topics. So here's kind of what a document would look like for LDA. So the colors here indicate the Z that goes along with each word. We have these K topics, these K multinomials over words, and they've been labeled, right? So we've given sort of some human has gone through, probably David Bly, and assigned labels to these things, right? So this label, this green label called budgets, has things like provide and 400,000 and board and foundation and so on. And we can also look at the underlying generative probability. So this is basically looking at that distribution theta d associated with a document, and we can see it sort of mostly seems to be, over a handful of different topics, arts, budgets, children, education. Here we can look at those individual multinomials, right? So now we want to look at this picture. We're looking at these guys. So there's a bunch of different multinomials. Maybe they were like 30 or 50 in this case, and David's decided to show us a few of these, 4, okay? So given that you've chosen, topic 13, right? So initially that didn't mean anything, but the words that are most likely given topic 13 are these ones. So this is some sort of like arts or entertainment kind of thing, film, show, musical, actor, opera, all right? And given budgets, it's million, tax, so on and so forth, okay? So that's LDA. It's an important model. It uses a lot of the techniques we use in machine learning. It's worth spending a little bit of time talking about it computationally. So this lecture, I'm basically talking about all the computational aspects of LDA. So last Tuesday, if you remember, I told you one algorithm for doing this, sort of a vanilla algorithm, Gibbs Sampling. And today I'm going to talk about all sorts of clever ways that people have come up with over the last 15 years to do that faster and better, okay? So the first thing is a technique we've already studied, okay? So we've studied iterative parameter mixing, where we basically take data, we shard it, we learn something in parallel, and then we combine the parameters. So you can do that with LDA. You can do it with many different things, but you can certainly do it with LDA. Kind of the first paper on this came out in like 2008, 2009. This is the journal version, so the earlier work was a little bit before that. So by these smart guys at UC Irvine, all right. So here's their basic intuition. So when we think about this model here, okay, there are really 2 sets of parameters we have to learn, okay? And let's, for the sake of argument, let's assume that we distribute the data in what's kind of the most obvious way, right? Our data is a bunch of documents. The obvious way of distributing it is to take each document and put each document on a different machine, okay? So every machine has its own local set of documents, a subset of the corpora, right? So there are 2 sets of parameters we have to worry about. One is these document-specific distributions, all right? And those are kind of easy to distribute, okay? Because this is specific to a particular document. All the counters we use for estimating that are specific to that particular document. So they all live right where that document lives, okay? You can localize those easily on one machine, okay? These guys, it's less obvious, right? So this is basically a distribution of words given a topic, right? And this is clearly shared by all these documents, right? So if I parallelize, I have to figure out, what are the implications of that, right? So what does it mean? So there's basically sort of 2 dependencies here. When I sample Z, a latent variable, a topic for a word, that depends a lot on the other document, or other Z's in the document. So if I'm looking at a document like this one, okay, if I'm resampling one of these words, say this one, okay, I know from looking at all the other words in this document that this document is almost overwhelmingly composed of just these 4 categories. Okay, most of the words in this document are one of these 4 categories. So there's a pretty good guess that this new word is also going to be in one of those 4 categories. So there are really strong dependencies between the classes in a document, and that's kind of what you expect. I mean, really what we're doing here is we're clustering the words. We're sort of assigning labels to the words, and the things that pull the clusters together is if you have the same instance, the same word token, then it's probably going to be in the same class or a small number of classes. And also words in the same document tend to be drawn from the same set of classes, okay? So there's a pretty strong dependency on other words in a document, okay? And there's a much weaker dependency on the other Z's elsewhere in the corpus, okay? Or maybe that's weaker, okay? So really this depends on the probability of a word given a topic. Okay, so we've already chosen a topic with what's the probability of the word given a topic? Well, that does depend on all the other variables in the corpus, right? So it depends on how many times that word has been assigned to that topic versus other topics. Okay, and that will change when we flip, when we resample latent variables in other documents in the corpus, but it's going to change pretty slowly. Okay. So the basic idea is maybe we can sort of rely on that and sort of keep these this part of the distribution locally and do my parameter sharing, parameter mixing thing on these parameters. All right. So this is the basic idea. So technically, if you try and parallelize Gibbs sampling with this sort of parameter mixing, all the convergence results sort of fall away. They don't apply any longer. So Gibbs sampling is sequential, not parallel. But you can just do it anyway and see whether it works, okay? And, spoiler alert, it's going to work, okay? So they have this thing called approximate distributed LDA. It's approximate because we're trying to do Gibbs sampling, but we're not really doing it, okay? So what do we have? We have, normally we've got the words X, the topics Z, and we've got some counters. Okay, so K here is a topic, so this is the number of times this topic has been assigned, I guess, to document J that's hosted by machine P. Okay, and this is the number of times word W has been assigned to document K by machine P. Okay, and then we've got our smoothing parameters. Okay, so this is what we need to run LDA locally. All right, so this is basically a copy of the overall counts on how often words have been assigned. Okay, so what we're going to do is we're going to look at basically parallelizing or distributing and then remixing are these counts, which are basically the number of times each word gets assigned to each topic. So those things are going to be we're going to allow them to drift locally, and then we're going to resynchronize them at the end of each cycle. So basically what we're going to do in parallel on each machine, we're basically going to run Gibbs for a while. Okay, and that's going to mean that we're going to get a different number, different numbers locally for the number of times a word gets assigned to a topic. All right, and after I've done that, I'll synchronize. Okay. And here we would use all reduce or something like that to merge all the global counts. So we'll merge all these so we get a one kind of summation of all these values. Okay, so that's the basic idea. Here's some a little bit of analysis, and here's a little bit of experimental results. So LDA, okay. Basically, so this is the time for one iteration. So n is the number of words in the corpus. So in one iteration, I'm going to go through, I'm going to flip a topic assignment, right? I'll resample a topic for every word in the corpus. Okay, to resample, maybe I should have put this code up earlier because you saw this last week. But to resample, what we do is we compute some probability distributions, all right? And then we basically go through a loop where we sort of like, we draw a number between 0 and 1, and then we figure out what topic that corresponds to, right? So this turns out to be, in the way I described the implementation in Python, linear in the number of topics k. All right, so it's linear in the corpus size, linear in the number of topics. That's not so bad. Okay, and what we have to keep is basically we have to keep one topic assignment for every word position. Okay, so that sort of is something we might need to hold. All right, and then for every topic, we need to know how many times that topic has been assigned in a document, and how many, what's the kind of interaction between the topics and the words. So if W is a number of word types, this is sort of the space for LDA. Okay, and the time is linear in both of these things. Okay. So here we've got something a little bit different. So this assignment, this here is the assignments to the well, actually this is not really the assignments. We don't have to worry about that. This is the actual words. We have to store the words. All right. So we're taking those words, okay, and we're also taking the document specific distribution, the document specific counts, and those get distributed across P different machines, so this gets smaller. Okay, then when we synchronize, we still have to synchronize all the multinomials, the word multinomials. So there are k of those, and we've got a parameter in each one for each word. So that's kw, all right? And then this is the time. Again, this nk sort of gets split by 1 over p. We still have to do this kw step, that's the synchronization step, and then there's some overhead for communication. All right. So this suggests we should be able to get a pretty good speed up if, of course, it doesn't turn out that doing this causes us to take a lot more time to converge, in which case maybe we lose. So these are some corpuses that they used, some corpora. So these are various different sizes. I guess the biggest one here is Wikipedia, which has 300 million words. Okay, and let's look at some numbers. So these are two of the smaller data sets, and what they did here was they did an experiment with different numbers of topics. Okay, so each one of these lines is a different number of topics. All right, and on the x-axis here we have a different number of processors, going from 1 to 10 to 100 to like 1,000. All right. Okay. So this is basically what the overall perplexity is. So that's how well the model fits. So to measure perplexity, you take a test set, you look at the number of bits, the average number of bits to encode each token, given your model. So it's a measure of how well the probabilistic model fits the data. Okay, and we can sort of see two things here. One is it doesn't look like the parallelization is hurting us too much. So sometimes we sort of get a little bit lower perplexity, so it's not quite as good with more processors, but it doesn't sort of seem to be a very clear trend. Maybe you can sort of see it dropping off here. Okay, but it definitely looks very flat when you've got lots of topics. Okay, so we can so that parallelization is not really hurting us in the sense that we're still getting, models of similar quality. The other thing is we can also see that for both of these things, actually, it's good to have a lot of topics. Okay, so the biggest way of getting better perplexity is just adding more topics. So we'll come back to that. Here's some other results. So the algorithm I just told you about is called ADLDA. HDLDA is another algorithm that's described in that paper, which I won't kind of go into. So it's sort of more of a mixture model, it's more of an ensemble of LDAs rather than sort of a real LDA. So these numbers here are convergence rates for LDA. So this circle is LDA, and this is with 10 machines, and the one below that is 100 machines. So basically the short story is, again, we're converging pretty quickly in terms of the number of iterations. So it's not, the parameter mixing is not hurting us here too much. Okay, finally, we also see this is the amount of speed up you get. All right. So this would be a perfect speed up. So every processor you get gives you the same amount of speed up. So if I have 100 processors, it's 100 times faster. 1,000 processors, it's 1,000 times faster. Okay, so that's the best you could hope to do. And in reality, you're never going to do that because there's going to be some sort of communication overhead. But going up to 1,024 processors on Wikipedia and PubMed, they're two big corpora. You're getting really good speedups. So you're getting speedups of several hundredfold. Okay, so that makes LDA a lot faster. Okay, so when these results came out, and I think a lot of other people were kind of surprised. Maybe in retrospect, we shouldn't have been. But there's kind of a big difference between parameter mixing for classifiers and parameter mixing for this sort of topic model case, which is that when you're looking at this sort of unsupervised data, the topics don't have any intrinsic meaning. So when you're looking at the multinomials for a supervised or a semi-supervised naive Bayes class, there's one multinomial which is the words given that you're in the Economist's website, and there's another multinomial of words given that you're in the Onion website. Okay, that's what those things mean. Okay, when you're doing an unsupervised, you've got topic 1 and topic 2, and there's no reason why those things can't be switched. You could certainly permute all the topic numbers and you get a model that was just as good, right? So it sort of feels like when you parallelize and you sort of don't coordinate those sorts of assignments, you'd end up with all sorts of horrible mistakes. But it turns out to not be true. Okay, in most of these experiments, they did a little bit of sort of pre-processing, so they kind of see the topics by doing a little bit of sequential work on a subset. But that's sort of enough. So that was kind of a surprising result. So LDA is something that they use all the time in industry. Okay, I know there are implementations of this for that are available for Mahout, which is Hadoop. There's one that is used at Yahoo. There's one that's used at Twitter. So the kind of standard technique is to do this sort of parameter mixing, okay? And this is kind of way a lot of the techniques work. The technique that I talked about on Tuesday, where you distribute the parameters with a parameter server. Again, you're basically doing, you're using sort of special purpose code for synchronizing the global counts, and you're avoiding a lot of reads. That's generally a faster approach, but it's still essentially the same sort of model. You're still delaying that synchronization. So this is one of the stories. You can parallelize by basically just running these samplers in parallel, and that seems to work pretty well. So are there questions about this so far? All right, let's jump into the next thing. All right. So we can run things in parallel, but we can also try and use a little bit of computer science to make what we're doing faster. Okay. So these are some of the tricks of the trade for fast sampling, and this is in the context of latent Dirichlet allocation. For this course, I'm making this very concrete, but a lot of these techniques are very general. So sampling is something you do a lot in machine learning, and Gibbs sampling is something you do a lot, and these techniques are kind of worthwhile knowing. So since this is kind of low-level detail, this is kind of pretty detailed. Let's sort of spend a little bit of time kind of swapping the algorithm in. Okay, so this is my kind of pedagogically simple description of LDA in Python. So I've got x sub d sub j is the word that's in document D at position j. Okay, so that's going to be some index in the vocabulary. It'll be some big integer, you know, if there's 10,000 words, it'll be between 1 and 10,000. Okay, Z is the latent topic. Okay, so there'll be many fewer topics than there are words in the vocabulary. Maybe there'll be 100 topics. Or if it's a big corpus, maybe 1,000 topics. Or a really big corpus, it might be 1,000,000 topics and, you know, a few billion words. But it's going to be many fewer than the number of words. Okay, we got some representation for, you know, that tells you what the word is, giving an index. All right, and then these are the counters I'm going to keep track of. Okay, one is the total number of words in the corpus. Okay, one is the number of occurrences of word W that have been assigned to topic K. One is the number of words in document D that have been assigned to topic K. All right, and then we also sort of have this marginal here. So this is the total number of words that have been assigned to topic K. All right, so these are counters. All right, okay, these ones are the document specific counts. Okay, and these are the word specific counts. All right, and you know, to compute probabilities, I need the smoothing coefficients and I need sort of the denominators of these, and you know, the total number of words assigned to a topic is the denominator for this. The denominator for this is the length of the document, so I don't have to keep that separately. I can sort of get it out of these data structures. Okay, so there's two basic processes. So one is you basically go ahead and you randomly assign things to a topic. All right, let's not go through that. That's kind of boring. Okay, then the algorithm is basically I go through every document. I go through every position in that document. Okay, I choose randomly a new topic for that according to the right probability distribution. And then I update my counters. So flip is basically going to update all the counters. Again, I'm going to skip what flip does because it's not very interesting. It's just moving some counters around. But here's what we're basically doing. Okay, so what we're computing here in this resample step is something like this. Okay, okay, I've got this little offset here. So this is whether the position J of document D is in topic K or not. If it's currently assigned to topic K or not, right? So this is a little offset that I'm going to do to modify my counters. Okay, so if I take n sub kd, this is the number of times topic K appears in document D, and I subtract that magic number, okay, that will tell me what's the probability of getting that topic in that document, okay? And the other part of the story is I want to figure out what's the probability of, so this is the probability of seeing that topic given that document, and the other thing I want is given what's the probability of seeing that word given that topic, okay? So that's basically the number of times that word has been assigned divided by the total number of times that word has been assigned to that topic. Okay, right, or the total number of words assigned to that topic. All right, so that's this total count right here. Okay, and then there's this little offset we have to subtract to both of these things and the smoothing. Okay, so basically at the end of the day, I've got AK and BK. A is this part, B is this part. Okay, this is kind of the upstream probability, the causal influence. This is the downstream probability. Okay, we want to pick from something that's proportional to those two guys. All right. And you know, first I have to compute all those numbers and then I have to choose. Okay, so here's where I randomly pick from that. It turns out the way I do this is I have a bunch of these guys. I know what the value of A times B, AK times BK is for each of these topics K, right? And I'm just going to scan through this linearly. At each point I'll sort of keep track of the cumulative probability, all right? And then when I get to something where, you know, the cumulative probability below me is less than the value I chose, okay, and the cumulative probability above me is more, then I say, okay, that's it, topic 3. I pick topic 3. So you sample by picking a number between 0 and 1, okay, and then you do a linear scan through the topics, okay, after you've computed their values, okay, and that's certainly the obvious thing to do, okay. If you look at the runtime, you know, if you ran this through a profile, you would see that you were spending all your time virtually all your time resampling, okay? So that's what happens in a Gibbs sampler, resampling, okay? This is linear in the number of topics and linear in the number of words, okay? And that sounds good, except overall, it's not so good. So overall, the problem is, as you get larger and larger corpus, you need more topics to model it. So if someone gives you like a little corpus of a few hundred emails, you can do LDA with 10 topics and you'll get something reasonable. If someone gives you all of Wikipedia and you try and squish it into 10 topics, you'll get really messy looking results, okay? You really need a lot more parameters to model the kind of interesting distribution you see in a large corpus. So essentially what happens is the number of topics is going to grow with the size of the corpus. So really this whole thing is really worse than linear. How much worse than linear? It's kind of hard to say. I don't know of any rules like the number of tokens in a corpus of length n is about square root of n. I don't know of any rules like that, but it's certainly going to get bigger, okay? So it's also not obvious how to fix this, right? So the problem is we're doing this linear scan, right? And it's not obvious what you can do beyond doing a linear scan, okay? So basically, until you get to this position in the document, right, that depends on all the other assignments in the document, right? You basically have to recompute these, okay? And once you recompute these, so this is something new, right? You can't do something fancy with this list of probabilities because you don't have it before, right? This is something that's being computed every time you go through the sampler, every time you resample, okay? So what can we do, right? How can you speed this up, okay? So it was actually a few years before people started realizing that they could speed this up. The first paper I know about that really looked at this and sort of made a big improvement was work by David Vimno and Andrew McCallum. Let's just kind of step through what they did. One of these days, I'm going to take this lecture, I'm going to turn it into lecture notes, and when I do that, I'm going to standardize the notation, because everybody that's published a paper on this in the last 5 or 6 years has used slightly different notation, and I'm sure it's driving you all crazy. But I haven't done that yet, so we'll just have to kind of deal with it. So this is Vimno's notation for the sampling step, okay? So this is basically the same thing I wrote. So what's this? So this is the smoothing parameter alpha and beta, okay? And this is his notation for counts. So this is the number of times that topic T is assigned in document D. So he's using T for a topic and W for a word, okay? So this is the number of times that topic has been assigned in the document, and there's a proportionality here, so there's a normalizer, okay? And that's sort of the upstream probability, that's the upstream score, okay, the causal influence. And then here's sort of the evidential support, right? So beta and beta V are the smoothers, okay? And this is the number of times that word has been assigned to that topic. Okay, W is the word, T is the topic. And this is the total number of times any word has been assigned to that topic. All right, so these are the same, variables, the same counters, just slightly different notation. I apologize. All right, so this is what we want to compute, okay? So this is the idea. We're going to take this and we'll just distribute, okay? So we'll take this thing and just distribute it over everything and we get this term, okay? Then we'll take both of these guys, I'm going to take this one and distribute over this first part of this and then also distribute over the second part, okay? So this whole probability is just the sum of these things, okay? Just algebra, okay? I don't know why he thought to do this, but, and it's not obvious why this is a useful step, okay? But that's the basic idea, okay? So we can now think of the sampling process. So I'm sampling according to these values, okay? We've got one value like this for every topic, right? Okay, we've got one value for every topic, which means I got one of these, and one of those. Okay, so let's actually take these values for all the topics and just kind of regroup. Okay, so I'll take all these guys and add them up, all these guys and add them up, and all these guys and add them up. Okay, if you want to think of what we've done is we've basically taken, in this picture here, these little boxes. I've taken each of those boxes and I've broken them into 3. Okay, and I'm taking all the first third boxes, all the second third boxes, all the last third boxes. All right. What I'm going to do is I'm going to use that grouping. Okay. So together, S plus R plus Q, after we normalize, have to add up to 1. Okay. So that's clear. Okay. So if I just add these things up and then divide by that, I kind of know what how to normalize. Okay. But there's also sort of like a trick here. Okay. What I can do is I can draw a number between 0 and 1. Okay. And then I can figure out whether it's in one of the first third, one of the second third, or one of the third thirds. Okay. So I've got top, middle, and bottom for each one of those topics. And I've basically combined all the top ones. Okay. So the first thing is if this is less than S. Okay. So if it's in one of the top thirds, after we combine them all, then I'm going to choose one of the top thirds. Okay. All right. So that's the first step. That's not this step right here. Okay. So these quantities also basically just depend on the number of times each word has been assigned to each topic and these smoothing parameters. Okay, so if it's less than S, basically what I'm going to do is I'll construct another little square, with tick marks at the appropriate sites, and I'll roll a coin, the second coin. The first one tells me I'm in part S, so it's one of the top third sections. All right. And the second one is going to tell me which one it is. Okay. So if it's less than S, I'm going to look up some number U. So my uniformly distributed random number in a square that has tick marks separated by this amount. Okay. So I basically sampled something. It happens to be sort of from the first third. Okay. So if it's in the second third, then I can look up U in the appropriate line segment here. Okay, so again, I've got a bunch of boxes, each are the size of the middle third for each of the topics, which means they're this big. Okay, so here's the cool part and why it makes sense to break things up this way. Okay, so this numerator here is the number of times topic T has been assigned to document D. Okay, so imagine I've got 1,000 topics, and my document has, I don't know, 100 words. Okay, so only 100 of those 1,000 topics can be assigned, even in the worst case, right? There's only 100 positions, and there are more topics in that. So 90% of these numbers are going to have to be 0. Okay, so I only need to look. Okay, I only need to construct this for the topics that have actually been assigned in that document, not for all the topics. Okay, so this part of the loop is no longer over all the topics. It's just over the topics that have non-zero mass in the document. Okay, so depending on how you smooth, that might be a relatively small set. Okay, and if the documents are short, it's always going to be smaller than the number of topics. Okay, the documents are short and the corpus is big. Okay, so if I'm picking something up here, then I've got to win. Okay, I don't have as many line segments. I don't have as many tick marks to go through. So I'm scanning through something that's actually smaller than the list of topics. Okay. And then there's another possibility. It might be sort of in the bottom third. Okay, the last third. All right, now I'm sampling from here. Okay, here again, in the numerator here, we've got sort of a nice story to tell. Okay, so in the numerator here, we're multiplying by the number of times this word has been assigned to a topic. Okay, now, again, there are going to be some words that are very frequent, and they're going to be assigned to lots and lots of topics, perhaps. Okay, but maybe after you've been learning for a while, a word is going to converge to maybe a small number of topics. And more to the point, most of the words in a corpus are not that frequent. Okay, we know there's a long tail of words that only appear once or twice or 3 times. So, I mean, practically when you do LDA modeling, you often throw away the least frequent words and throw away stop words because you get better results as well as making the thing faster. But even after you do that, there'll be lots of words that only appear, I don't know, 100 times or 200 times or 50 times or 25 times, right? So there'll be a lot of infrequent words. And once again, those words cannot be assigned to all the topics, okay? So we've got another loop here, but we only have to check this on the words that have been assigned, on the topics that have been assigned at least once to those words, okay? So what we now have is we now have basically 2 sparse lists here. So this one is sparse because it's limited by the length of the document. This one is sparse because it's limited by the number of times the word appears in the corpus. Okay, so so that's the basic idea. Okay, so we're doing the same sampling trick, but instead of having to loop over every topic, okay, we've got 3 loops that we do. One is over the total number of topics that word has been assigned to, so that's limited. The other one is the total number of topics that have been assigned to that document, so that's limited, okay? And then there's this one, which is not so limited, okay? That one's actually still over every topic. So asymptotically, we haven't helped ourselves too much, but you know, depending on the smoothing parameters, this actually turns out to be not that frequently checked. So it actually gets checked about 10% of the time. All right, so we could get a big speed up still. All right. The other thing that's a big win here is the amount of space. Okay, so so this gives us some insights into what we need to store. Okay, so here I have to store the total number of words per topic, which isn't too bad, right? It's like for every, you know, the number of topics, linear in the number of topics. Okay, and just these, you know, smoothing parameters. Okay. Here, what I have to store is basically the number of times, the only new thing I have to store is the number of times each topic has been assigned to each document, right? There's kind of a trick that we can do here since we're going through the sampling process document by document. What I can do is I can basically not store these counts explicitly. Instead, I can basically compute them on the fly when I start working on D, okay, and then update them incrementally, okay. What you can imagine here is that you're iteratively scanning over the corpus of documents. You have in that corpus the latent assignments to each word, okay? And when you load in a new document, you compute these totals, the total number of times each topic has been assigned, and you never actually store that. So the actual storage for this is sort of zero incremental storage if you're already storing the latent assignments, okay? And then here, okay, so here we've got to assign this number for every word topic pair, okay? So that's the killer, okay? But again, we can sort of exploit some sparsity here, okay? So what we're going to do is the following. For every topic, we're going to pre-compute this, okay? So this gets pre-computed when we start, when we open our document, okay? All right. And now what I really want to do is I really want to find, I don't want to just find which these are non-zero. I want to find which ones are where this quantity is large, all right? Okay. So if I want to find out where this is actually a large number, all right? So here's basically the idea, okay? So for every word, we're going to get these counts are going to be stored in an array. Okay, the worst case is the size of the number of topics, okay? But we can also limit it by the frequency of that word, okay? So for every word, we allocate an array to hold these things, but it's smaller for sparse words. And it's only full size for the words that are the size of the topic, okay? Now, what I want to do is in my sampling, okay, when I'm scanning through this list, let's go back to this picture. I should have put this up somewhere. This one, okay? So what I'm going to do is I'm going to pick a number and then I'll scan through these things. So it would be better if I basically had the big ones early, because then I'm much more likely to sort of just scan a short period of time. Okay? And there's also going to be this sort of like skewed set of values. Once we've done some training, words are going to gravitate to like a small number of topics. Okay? So it's also helpful if I can find the big ones quickly. All right? Okay? So what I'm going to do is I'm going to keep it sorted. Okay? And Mimno, being a little bit of a hacker, decided to do it this way. So we've got a topic number and then a number of times the word occurred in that topic. Okay? And those are just stored as one integer. Okay? So n is in the high order bits and the topic number is in the low order bits. Okay? So let's say there are 1,024 topics. We just say 10 bits for the bottom, right? And then we have, whatever, we've got 64 bits or 20, so we've got, maybe another, if we're just doing like 32-bit integers, we've got another 20 bits, 22 bits to model the, I'm sorry, let's see, for the counts, all right? So we'll basically keep it as an integer. The corpus isn't big, 32 bits is fine. So certainly 64 is more than I'm going to need, okay? And then to get these things in order, all I got to do is sort them out, okay? If I sort them, they'll be sorted by frequency order, okay? So, so what we do actually is we keep these things sorted, and whenever I flip a bit, of course, I'm going to have to update those counters, all right? Which means that the sort might be off, okay? So what Mimno did, and I think it's the first time I've seen a bubble sort appear like, like in a KDD paper or something like that. But what you want to do is you want to just basically fix up that sorted list. So experimentally, what seemed to work best is to just do a bubble sort. You basically scan through and there'll be a few things out of order and you'll fix them up. And again, a lot of these things are small and sparse. Okay, so it's not so bad. So we basically compressed our storage a lot. And now our count updates involve doing these like bubble sorts on small integer arrays. Okay, so how much does this help us? So, so this is basically seconds per iteration. So this is the old LDA, linear in the number of topics. This is the new one. Okay, so we can see it's a lot faster. This is memory in megabytes. All right, again, linear in the number of topics. I don't know why it's falling off here. Okay, and then still linear, but much faster. Okay. So that's basically David Mimno and Andrew McCallum hacking LDA to be much faster. Okay. And like I said, this was like the first thing, and everybody uses sparse LDA now, right? You would not use that sort of data if you're doing it seriously. But there's something a little bit unsatisfying about that. So it really is just a trick, right? So the sampling is, maybe it's like 10 times faster or something, but 10% of the time you still have to scan through all the documents, right? So the sampling is faster, but maybe we can get a little bit further. So maybe there is some clever data structure that we can use. And you got to remember, there's sort of two things we have to worry about here. We have to have a data structure that's easy to update when I resample. So when I flip one latent variable from topic A to topic B, okay, I've got to be able to update all my data structures quickly, all right? But I also want to be able to sample from them quickly, all right? So let's look at this picture again, all right? So so here I've got a multinomial. These are the kind of probabilities. So 1 out of 4 of getting this light blue and 1 out of 5 of getting this yellow, 1 out of 10 of getting this gray. These are the cumulative probabilities down on the bottom. That might be kind of helpful somehow. All right. So the algorithm we've talked about so far is the following. We keep them sorted like this, okay? And then I pick a number between 0 and 1, okay? Yeah, half the time it's going to be sort of like less than 0.5, okay? And I'll only have to scan through, these bottom 2 or 3, okay? A quarter of the time. So if I keep these sorted, it'll be I'll be fast kind of on average, all right? But maybe we can actually do something faster, okay? So so here's kind of a proof of concept that you should be able to do something faster. So here's these are the cumulative probabilities, okay? So I'm going to basically take each one of these blocks, I'm going to put it in a tree, okay? And I'm going to order the blocks the same way, okay? So if you like sort of do a prefix ordering of the tree, then you'll get, 1, 2, 3, 4, 5, 6, 7, right? Okay? 5, 6, 7, right? So we'll get the same, we'll keep them in the same order, and we'll tag everything with its lower and upper bound, okay? So when I roll a number, when I choose a number between 0 and 1, my claim is I can actually find it quickly in this tree, okay? So this is a data structure I actually used a while back. I didn't know what it was called, but you can find it quickly in this tree. So let's say we pick a number like 0.6. All right, is it between the point 23 over 40 and 7/10? If it is, I'm done. Okay, if it's not, I go to my left. If it's lower than that, if it's below 2340, I go to the left and recurse. Okay, if it's larger than that, I go to my right and recurse. Okay, so eventually I'll find something that it's in, and I only have to do sort of log-in comparisons, where n is the number of topics I have here. Okay, so you certainly can do that faster. All right, maybe you could do it even faster than that. All right, so here's a kind of clever idea. So apparently this is an old data structure, but it wasn't used for topic modeling until a little while ago. So here's my simplified, and I just have like 4 boxes here just to kind of make things simpler. I want to sample from this multinomial. All right, so here's the idea. Okay, so what I could do is the following. Okay, so I said what I'm going to do is I'm going to basically just draw a number between 0 and 1, and then see where it lies on this, which might involve doing some sort of scan. Okay. Here's another idea. Okay, I'm going to take these things and I'm going to lay them out in 2 dimensions. Okay, right. So I'll just lay them out like this. That's a little bit of pre-processing time, but that's maybe okay. So now I've got this. Okay. So what I'm going to do next is I'm going to draw not 1 random number, but 2 random numbers. Okay? So conceptually what I'm doing, before I was like choosing a point on this like 1-dimensional line segment. Now I'm choosing a point in this square. So you can think of it as just like throwing a dart randomly at the square. Okay? All right, so I look at that. So when I put these things in the square, I made them all the same width. Okay? So I can look at this and see immediately which stripe it landed in. Okay? All right, so I can see immediately this was in the first stripe. Okay? Of course, there's another possibility, right? It could have missed, right? It could have not hit any stripes. All right, so I can see immediately this is on the 3rd stripe. Okay? Right, so it would have been yellow, but it's not yellow, right? It missed that yellow. Okay? But what I can do is I can do rejection sampling. So basically, I throw these darts until I happen to hit a non-empty part, and I can tell whether it's empty or not by looking at the height of that thing. Okay, so I can look at my y-coordinate and say, well, is it more than 1/12? It's like, yeah, it's too big, it missed. So let's throw another dart. Okay, so I can do this. All right, so that might be better or not, and I don't actually know because there's actually a way to take this and fix it up so it's even smarter. Okay, so here's the idea. Okay, so I'm going to keeping this idea of basically putting these things like a 2-dimensional box and throwing darts at that box. All right, but I'm going to try and reduce the amount of space. Okay, so I've got a lot of brown space here that's a miss. I'd like to reduce that. It could be a lot, right? If we've got like a few big numbers and a bunch of really small numbers, it could be that most of the space is missing. And I spent a lot of time throwing darts without hitting anything. So what I could do is make the height of this box different. Okay, so instead of making it the height of the largest number, let's make it the height of the average number. Okay, so the average value here. Okay, instead of doing this, okay, what I'm going to do is I'll figure out what the average is, okay, and then I'm going to basically just sort of like move things around until, with the hope of minimizing this this coverage. So here I can actually get it so everything is covered, okay, and furthermore, I only have 2 stripes in each vertical section, right? So I only have 2 different colors in each vertical stripe. Okay, so it turns out you can always do this, all right? You can basically prove that this, that this structure is always possible to do, okay? So you'll never waste any space, so you'll completely fill this thing, and you only need two things. You only need two different colors in every stripe, okay? So it's a simple data structure. The algorithm is not that complicated. It's called an alias table, all right? So now, basically, I've eliminated the inefficiency, okay? I know exactly where everything, what color I've hit every time I throw at this, I throw a dart at this, all right? I just have to check what vertical stripe it's in, okay, and they're all the same width, so that's easy. And then I just have to check to see whether it's the bottom or the top one. So I just basically need two labels and one threshold test, okay? So it's really easy to see where the dart hit. There's no wasted space, so the dart never misses. That was supposed to be a joke. I'm sorry. Yeah. So mathematically, the dart never misses. Okay. So here's the idea. So this is a paper by Alex Smola and some colleagues from a couple of years back in KDD. So you can sample really quickly, okay? But it takes linear time to build this alias table, okay? Linear in the number of topics, which is exactly what you're trying to avoid, okay? And once you flip something, once you change one topic assignment, your alias table is wrong now, okay? So you have to regenerate it. So what they did to avoid that is they used another little trick. So rather than just use an alias table once and then try and patch it up or redo it, basically you draw from it many times. So you'll draw from it maybe 1,000 or 10,000 times. So you only update it occasionally. And you can compensate for the fact that the parameters are stale. So there's a technique called Metropolis Hastings. It's related to Gibbs sampling, but the idea is there are basically two distributions involved. So you're actually drawing from this distribution called Q, which is a proposal distribution. So this is something you can sample quickly and easily from, okay? We could, for example, use an alias table here, okay? So we can sample from that quickly, all right? Then after I've sampled, we do a little bit of a check, okay? So P is the correct distribution, all right? And we basically look at this sort of threshold, okay? So if P and Q are pretty close, all right, then this is going to be pretty close to 1, and most of the time you're going to sort of accept your flip. Otherwise, you know, you might reject it and you'll have to kind of continue. Just to kind of make this concrete, so these I's and J's here would be vectors of topic assignment. So when we sample, we're basically choosing a new topic assignment given the last topic assignment. So this is my sampling step, all right? And Q is the old alias sampler, and P has got to be based on actual count. So this is sort of the revised number. So I can evaluate the probability of something relatively quickly. It's just hard to sample from it because that involves kind of a loop over the topics. So this is the other idea, and this is again another kind of clever idea to use, right? To kind of trade off rebuilding the data structures you need to sample with the cost of basically doing a little bit of rejection sampling. So this is a very controlled way of doing that. And again, this works. So this is seconds per iteration for these two different algorithms. So we can see that the alias LDA is faster. Not quite as dramatically faster as we saw before, but it's faster. Okay. This is this is just for two different data sets, right? Okay. So particularly in the earlier iterations, the alias LDA is a lot faster. Probably because the sparse LDA gets a little bit more concentrated. So after you sort of know what topics look like, words are going to be concentrated in fewer topics, and fewer topics are going to be assigned to a document. So over time, the sparse LDA gets faster. Okay. This was the lecture I gave on fast LDA algorithms last year. This past year, I found yet another kind of fairly recent cool paper. I think this was from last year, maybe 2015. This is from some very smart people. Vichy is out at UC Santa Cruz, and Indrajit Dion is at UT Texas, and some other folks. This paper also has two ideas. I'm going to spend most of my time talking about one of them and just kind of gloss over the second one. A while back, I talked about this data structure, all right? So let me kind of go through the basic idea again. I've got this multinomial, all right? I want to sample from it quickly. So how could I do that? Well, one possibility is I sort of compute the cumulative probability of all these numbers, right? So I now know, the sum of all the probabilities to the left of this, up to the right-hand boundary of this blue one, and all the probabilities up to the right-hand boundary of this yellow one, and so on and so forth. Okay. What I want to do is I want to find the thing that I've rolled. I want to find the vertical stripe that corresponds to the point on this line segment that I chose at random, and I want to do it quickly. So we can do a tree, okay? So once again, I'm just going to take the things on the line segment, I'll put them in a balanced tree, okay, just left to right, okay? And the way it's going to work is each node in this tree has got the left boundary and the right boundary, okay? And I look at the number that I've drawn, and I decide whether, if it's sort of between those things, that's the stripe I chose. If it's smaller than that, I go to the left child and recurse. If it's larger than that, I go to the right child and recurse, okay? So this is log of the number of topics instead of the number of topics, okay? A few more comparisons, so it's log 2k. So that's actually a data structure. Like I said, I kind of stumbled into this. I implemented this a few years back and connected with some other code. And I wasn't quite sure what to call it. But it's called a Fenwick tree. It was invented by this guy in 1994, back when I was a small child. So the one thing that's nice about this paper by Dion and his friends, Dylan and his friends, is he actually gives you sort of a breakdown of a number of different ways based on pretty much kind of standard data structures that you could solve this problem. Okay, so the first one we looked at was basically linear search. Okay, so we just basically know these probabilities. They're not necessarily ordered in any way. Here there's like biggest to smallest, but they could just be completely randomly ordered. And I can get through, I can figure out where I landed by rolling a number in linear time. I just scan through this, sort of keep a running total of everything, okay? That's a reasonable approach, okay? There's basically, the initialization time is minimal, okay? The time to generate is linear in the number of topics, okay? But the time to update parameters is very fast, so it's got some pros and cons, all right? Another possibility is to pre-compute the kind of cumulative scores, okay? So pre-computing takes a little bit of time. I've got to scan through it once to get those sums, right? But once I've done that, okay, then I could actually, here's another way I can actually, like an obvious way of like figuring out where I've landed in this thing. I can basically just do a binary search and find out where I am. So the binary search is a little bit funny because you're looking for something that's to the left of you and then also something that's a little bit larger than you. But you can basically modify a kind of standard binary search to figure out where in this section you've landed, right? You basically just need to store these numbers, okay? And if I choose a number like say, 0.6, I basically do a binary search to figure out which of the numbers in this list which is the largest number smaller than it and the smallest number larger than it, and then I'm done. Okay, so you can do binary search, okay, same amount of space, okay. It only takes log time, logarithmic, and number of topics to update it. but it takes a little bit more time to update the parameters. Okay. So then there's the alias sampling that we talked about, right? So you know, do this thing and you throw a dart. Okay. So so generation time is super fast, but update time is actually linear. Okay. So that's got trade-offs. And the last thing is this tree. Okay. So we can keep basically a balanced binary tree. One thing that's nice about this is actually you can update these things relatively efficiently as well. Okay, so it turns out the update for a Fenwick tree is also logarithmic. So you can sort of traverse down this tree if you're basically, these things are going to basically be counts, right? So you can basically traverse and find the topic that you need and update those counts. Those are basically 4 different data structures. They have different trade-offs. And now that we sort of understand that, we can look at the sampling problem that we have and make some intelligent choices about where to use which algorithm. Okay, so they do a similar sort of decomposition, not quite as detailed as the one they use in sparse LDA, but essentially there are 2 steps here. One, this is basically sort of the document-specific topic distribution. Okay, yeah, so this is the document-specific topic distribution. Okay, the way they've set this up, this also includes the smoothing parameter, so it's never 0. Okay, so this is a dense distribution. Okay, but it also changes slowly. Okay, when you flip something, it changes slowly, and you reuse it many times because you can reuse it for each word in a document. So they use a Fenwick tree for this. All right. So for this case, we've got a sparse array. This is just an array that's limited by this number of the frequency of a word. Okay. You have a different data structure, a different array that's used for each unique term in the document. In kind of the standard way they do the sampling, they use a linear array for this in binary search, okay, which is kind of similar to what Mimno did, except he's using binary search instead of using a bubble sort and trying to keep the numbers big. Okay, so that's the basic idea. So this one is called R, this one is called Q, and again, we have the sort of this trick where you either sample from R or Q depending on the result of your first draw. Okay. All right. And here's some numbers. Okay. So this is looking at LDA on a couple of decent sized corpora with 1,000 topics. Okay. So this green line is sparse LDA. That's kind of the baseline. Okay, so alias LDA, so this number actually higher is better. This is the number of times you speed up, the number of times faster you are relative to a kind of a baseline LDA implementation that doesn't do optimization. So sparse LDA is like maybe 10 or 12 times faster, and of course much lower memory. The alias LDA is not as much faster. It's closer here, but they didn't reproduce smaller results in beating LDA, so maybe it's not quite as well tuned. These are the results for their system. Okay, so another thing they did, which I haven't quite fully digested and I haven't seen in other papers, but they also looked at 2 ways of doing the sampling. One is basically you do it the normal way. You go document by document, and you sample each word in a document. Another possibility is you can do word by word. Okay. So that has different costs because like different setups and so on, right? So basically you are doing small incremental changes when you sample for a word with respect to that, the word given document, the word given topic counts. You do that for every occurrence of the word in the corpus, right? And then you switch to another word. All right, so that's a different sampling strategy. They argue that for big corpora with lots of small documents, you should actually do better. in this setting, okay? It's doing sampling word by word because you're doing less sort of initialization on the fly, and that's true in their experiments. The other thing that they've done here is they've kind of broken this linear dependency on the number of topics that you still had with sparse LDA, and you really still have with the alias table because you're in the alias table you have to rebuild it every so often. So that lets them look at even larger numbers of topics. Okay, so before we saw 1,000, so this is their method, sampling by word, with 10,000 topics, okay, on the New York Times corpus. And this is sampling with 50,000 topics, okay? So we're seeing the speedups here going from, you know, with 1,000 topics, we're getting a pretty nice speed up, you know, of like maybe 5 or 10, okay? But when we go to 50,000 topics, we're getting, you know, hundreds, 100-fold speed up, or many, more than 100-fold speed up, okay? So that was the latest result, and right now that's my favorite sampling paper, at least for LDA. Just because it has a nice description of these like different techniques, and it looks specifically, so everything in the system is the same, the only thing they've changed is the sampling method. There's also a second part of this paper, which is kind of a cool way of parallelizing, and this is the one I was going to kind of gloss over. So, like I said, one thing you can do is you can sample document by document or word by word, right? You can also do something a little bit different. So here's as much as I'm really going to say about this. So in matrix factorization, we basically talked about taking our data. So there the matrix was basically users and items, right? So each row was a user, each column was an item, and we're looking at the rating a user gave an item. And we said, well, you can sort of refactor this by taking a sort of set of blocks and taking a diagonal strip of these blocks where each of these blocks are separate. If you do that, you avoid having any kind of conflicts, right? So these blocks can be parallelized quite nicely, okay? So in LDA, you don't have quite that same decomposition, but you can kind of approximate it. So here what they do is they take this, so again, so here what we have basically is words and documents, okay? So each worker gets one of these blocks, so it's a subset of the words and a subset of the documents, all right? But of course, nobody can quite finish, okay? Because each document has a different subset of words, all right? So this guy owns all these words. He owns all the words in this column, in these 4 columns. And this guy also has those words. This guy also has some of those words. So they can do some work, but at some point they're going to get blocked, all right? So what you do is sort of within this set of documents, within this worker, you go word by word. When you're done with a word, you say, hey, I'm going to pass this on to the next worker, okay? So what's happening is as you complete processing one subset of the words for your subset of the documents, you basically release that. It goes to another worker, maybe this next one, okay? So now this guy's got a different subset of words to deal with, okay? And what happens over time is this particular word is going to sort of migrate from worker to worker. So, and migrate from worker to worker basically means they're allowed to start working on it. They're allowed to start sampling it. So they call this the nomad algorithm. The words are kind of wandering nomadically from place to place. Again, here are some experiments. So this is sort of the speed up as you go from sort of 1 core to 4 cores to 20 cores. So you're showing, you know, again, pretty good speed up here in terms of the wall clock time it takes to get to some particular perplexity measure. Okay, any questions? All right, I'm just gonna like give you like a little bit of a taste. I started off by saying there are a lot of other models that are built on top of LDA. I'm just going to mention one because it kind of ties back to stuff we did earlier in class. So earlier in class, we talked about spectral clustering and modeling graphs. So I showed you all these pictures. And one way of modeling a graph is this idea of a stochastic block model. Okay, so you basically assign to every node in the graph some latent block. So for each person in this graph, there's some sort of latent social group that you're in. Okay, and then there's some probability that pairs in the same social group are connected, which would be relatively high, and there'd be some lower probability that people in other social groups are connected. Okay, so basically the parameters are basically what is the probability that someone from social group I is connected to social group J. Okay, and then you have to find those parameters, and you also have to figure out what the latent assignments are. Okay, so these are some graphs that are like sort of drawn like that. This is actually like football teams, and each color is a different conference. So the teams in the same conference play each other a lot, so the edges are whether a team played each other. This is a synthetic graph that looks a little bit like that. These are books that are like for, I guess, conservatives and liberals, and the green ones are kind of neutral, right? Here's a similar graph, you know, with kind of similar parameters, all right? So you can construct a kind of LDA-like model for that. So here's one. So remember I said basically you have to do two things. You have to assign for every node P a latent block, all right? And then for every edge, you basically, or every pair of nodes, you have to decide whether they're connected. So this is true or false depending whether or not they're connected. And that depends just on the latent block for each node, right? So here there's sort of two choices. One you make for every possible edge, one you make for every node. Okay. So this is a block model. Here's another one you can do. What does this look like? So what I'm basically going to do here is I'm going to generate all the edges in the edge matrix. Okay, so I'm going to think about the graph as basically just a long list of edges. Each edge has one node number and then another node number. Okay, so how do you do that? So you basically draw from some unknown distribution a block. Okay. And a block here is really sort of a pair of latent topics, one for the source node and one for the destination node. Okay, so these might be the same, they might be different. Okay, but you draw basically a pair of values I and j. Okay, from some smooth multinomial, and there's just one of those. Okay, and then given that, so given the latent value for I, you draw I. Given latent value for j, you draw j. Okay. And how are those things drawn? Well, they're drawn from a multinomial that's specific to that latent class. So you have a multinomial here where the things that are generated aren't words but are node IDs, and you've got one for each latent class. Okay, so this is really a lot like an LDA sort of model. You know, every document basically has just two words, a source and a destination word, and there's a different multinomial for the source word and not for the destination word. So that's sort of like one way of kind of thinking about what's happening. The sampling for this is pretty similar to LDA, and this is actually the algorithm that I showed you a while back. We're looking at comparisons of a bunch of things. So this is that LDA-like block model. Okay, these are various variants of the power iteration clustering, and these are these two kind of well-known spectral methods. Okay, so these were all social networks, and this was pretty competitive, but not always the best. This is a slightly different task, and again, these are pretty competitive with the kind of spectral methods. I'm about out of time, so I'm going to stop. So on Tuesday, you guys should all be here. We'll have some exciting talks by the project groups. I guess I'll see you guys then.